Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover something very special, which I know is probably the worst thing that students hate, and that is springs. So the basis of this tutorial is particle equilibrium. We'll use that to find all the forces, but we're going to take it a step further and use what we know about springs to find the displacement of the springs under those forces. And I find that once students kind of understand the spring formula, it's usually not that bad. But I know specifically I hated springs in undergrad. I hated springs in graduate studies because, well, I'll show you guys when we get to the example what we use springs for. But basically, everything in the world, it can be represented by a spring. And I'll show that shortly here. So let's begin. Alrighty, so looking at this question, what it wants us to do is determine the stretch in each spring for equilibrium of the 2 kilogram block. The springs are shown in the equilibrium position. So that equilibrium position part is very important because that indicates that the strings are already stretched. So before we get into this example, let's just go over a very important formula which you guys are going to need to know, and that is the spring formula. And for a spring formula, what the formula is it states that the force in the spring, so this is the force of the spring in, let's say, newtons, is equal to two things. It's going to be equal to the spring constant, which we call K, and then a factor which I like to call delta X. So this K is the spring constant, and usually you'll be given these. Spring constant, and it's constant for a reason, so it's always just going to be a single number. And then the delta X, that right there is the stretch length. And this is usually what causes so many problems for students, is the stretch length. Because when we're dealing with a spring, we have 3 different lengths we have to worry about. So in order to show this, to show you guys what the lengths are, I'm just going to draw a little picture for an example. So let's say that we have a spring like this. And let's say that in that position, the spring is unstretched. So this is unstretched. Stretched. And so what this means is that this distance here is the unstretched length. And what we're going to do for the unstretched length is we're going to label it L0. And then what happens is when we apply a force in compression or tension, it's going to stretch the spring or compress the string. But it doesn't matter which it does because the effects will still be the same. So if we have the spring and it is now stretched as so let's say it turns into this scenario, this new length right here, that's going to be our stretched, our total stretch length, which we're going to say L. And what happens is delta X, which is what we want, the amount it actually stretches compared to its original position, because remember this L right there, that's the new total length of the spring. That's not just the stretch length, that's the total length. This delta X, which we want, that stretch length, it's going to be L minus L0. So if we look in our diagram here, this distance right here, that's the distance we're interested in, that delta X, that stretched length of the spring. So in this question, when it says determine the stretch at each of the springs, what that means is it wants that delta X. It doesn't want to know the total length of the spring afterwards. It just wants to know how much should it stretch relative to its original position. So that's why we want to look at that delta X. So this formula, like I said, it's pretty simple. We have the force of the spring in one side, and on the other side we're going to have K times delta X. So in this question it's nice because what we're doing is we're really just solving for this delta X. And if we look at the rest of the equation, the K values are all given for each one of the springs. As you can see, we have KAC, KAB, and KAD. So K we don't have to worry about. The only thing we have to worry about is that force in each of the spring. But that's easy to find because we know how to do the particle equilibrium. So I'm just going to write particle, and then I'm just going to write EQIL, done. Particle equilibrium. So the only trick that you guys can really see with springs that would have to modify this formula is, let's say that they ask for the original length per se. They want this L0. So if that's the case, what you guys are going to do is you're going to write, you're going to write the force in the spring is equal to K. But instead of delta L, what we're going to write is L minus L naught. And what usually happens is you guys can solve for L right there. So we can actually solve for this L in this case by just doing trigonometry. So in this case right here, I'm going to do it in pink so you guys know. The stretch length of this spring, the complete stretch length, this is going to be the L there. And you can find that using the trigonometry. So that's not too bad. And then you can solve for that original length of the spring. So that's usually what you see maybe more in a lab or a midterm, but this question's nice. It just wants that delta X. So another thing before I move on is just the practicality of it. So when I was an undergrad, I hated springs. I hated springs because I thought, oh, these are like, who's going to use a spring in a building? And you're right. Honestly, we don't really use springs when we're designing actual buildings. However, when we model the buildings and try and find how much they deform or bend or anything like that, we use springs all the time. And I was actually quite shocked to learn this. So this is just for practical reasons. You guys don't really have to pay attention to this part if you don't want to. But let's say that we have a building here. And it goes something like this. And these are going to be just the floors and the columns. So if we have a building, and down here is the ground. So I'm just going to put this to say that's the ground. And we have two columns. Then we have the first floor. And then up top we have a second floor. What we do to model a building like this is we actually create points where anything intersects. So it intersects the ground here, the first floor here, the second floor, and over here we have another intersection, so something like this. And then what we do is we place springs between these points. So we're going to have a spring like this. Ta-da! And then another spring. And then coming across we'll have another spring. My springs are not the best, guys. I'm sorry. And then another spring. And you guys are starting to see what I mean. So this is nice because what springs do, as you guys can kind of see from this formula up here, is they relate forces. So the forces placed on the spring to displacements. So if we have a structure here and we know all the forces, we can start to figure out what the displacements are. And the only thing that we have to really consider is just that K value. So that K value, what we do is instead of having a small K value like a spring that we have here, like 30 newtons per meter, we'll have a K value for steel. So if we have a steel beam, we'll have a K value. If we have a concrete beam, we'll have a different K value. So depending on the material we use in the structure, we can modify that K value. And then since we know the forces on the building, we can start to find the displacements and how much it bends. But yeah, that's just my little speech about real-world applications. I don't want you guys thinking springs are useless like me, because I was in for quite a shock later on, and what you guys will find is springs are very, very useful. The only problem with using springs in the real world, which you don't see here, is in these cases, the spring constant K is constant. It's a constant value. However, let's take a concrete beam. As it cracks and starts to break, that K value is actually going to start to decrease over time. So it's not a constant value, making it really, really tricky to try and figure out that K value. But once you do, you can actually run a full analysis of a full building using that K value. So it's really nice. But let's get back on track and talk about our actual example here. So I'm just going to erase this stuff, because what we're going to do is try and find the forces in each one of those springs. Because remember here, if we have the forces and we know K, then we can start to find those stretch lengths, which is what we want. So it's really nice here, because if we look at point A here, we have all the springs intersecting that point. So that should be kind of a big hint to you guys. This should be my particle equilibrium point. So again, if I know that point, I like to draw a nice box around it. So something like this. And then anywhere that box intercepts is a force. So right here, I'm just going to draw the forces in a different color so you guys can see. Oops. Put the box back. Go over to here. Come on. There we go. So we can see that it intersects there. So there's going to be a force like that. There's going to be a force coming down here. And then, of course, there's going to be a force coming up here. So finding your free body diagram is an easy part, but it's a very important part, because without a good free body diagram, chances are you're going to mess up somewhere later in the question. So let's go down here and let's make that free body diagram for point A. So what I'm going to do is I'm going to draw kind of a dot, my particle, if you will, and this will be where all the forces intersect. So as we know, we are going to have three forces that intersect. So the first one that comes out like this. The second one's going to kind of come out like this. And we know that the third one is just straight down. So I'm just going to go straight down with this last one. So there's a couple things missing. One, we need to label all of those forces on the free body diagram. So the one in the top left over here, it goes from A to C. So what I'm going to do here is I'm just going to write force AC. The one on this side goes from A to B. So we're going to go force AB. And finally at the bottom, we're going to write force AD because it goes from point A to point D. So almost complete. The next thing that we're missing, of course, is our geometry. So what we can do is we can create triangles for all of these, for these two forces based on the geometry. So if we look, and I'm going to highlight right here, if we're looking at AC, so the left side here, we know that it goes 3 meters to the left and 3 meters up. So if we're doing a triangle, what it'll be is these two sides right here are going to be 3, 3, and then we could find the hypotenuse. But here's kind of a little trick. If both of those sides are equal, like we have in this case, and they're 3 and 3, what we can do is instead of putting 3 or whatever number it is, what I like to do, and what you can do, is just go 1, 1, and root 2. And because it's just very, very easy to remember. So we can do the same to the other side. So looking at the other side, it still goes up a distance of 3, but it spans horizontally 4 meters. So for this one, it still goes up 3, but it goes 4 meters. And just by looking at this triangle, we know if one of the sides is 3 and the other side is 4, the hypotenuse has to be 5. So the geometry is actually really, really simple. And even though our free body diagram looks done, we're forgetting one thing. It's just to put our coordinate system. So which way we're going to take the positive and which way we're going to take the negative. So for here, what I like to do is go right for positive as well as up for positive. So I'm going to go my X, my Y, and of course I'm going to put counterclockwise as positive. And that's for later on. So you don't have to worry about that too much right now, but later on it'll become a lot more important. So with the free body diagram, the next step, of course, is to write our equilibrium equations and then try and solve them all using, solve all the unknowns using those equilibrium equations. However, if we look at this, we can tell right away that we can't solve this, because remember that the rule of thumb is the number of unknowns that we have must equal or be less than the number of equations. However, in this case, we have 3 unknowns, so I'm just going to underline them in red. We have 3 unknowns, so we got FAC, FAB, and FAD. But we only have 2 equations, or sum of the forces in X and sum of the forces in Y. So what that means is we actually cannot solve this problem yet. So if we look at this, I'm just going to erase these, and what I'm going to do is I'm going to label this free body diagram number 1. And what that means is we'll use it later, but right now we can't really use it. It serves no purpose because we can't solve all of those forces. So that should be a big hint that there's another free body diagram somewhere in the question. I'm going to put that one as 2. So if we look up here, what we want to do is try and find another point that we can create a free body diagram for. So I'm going to do this in pink, and we got 3 options. We got point C, point B, and of course point D. If we look at point B and point C, they're connected to what we call pins. And these pins have 2 reactions. They're going to have a vertical reaction and they're going to have a horizontal reaction. And it's going to be the same on the other side. And we don't know those reactions. It's something that we'll cover later in the course, how to find those reactions. So, but what I'm trying to say is if we take point C or point B, we're just going to have more unknowns and we won't be able to solve anything. But if we look at point D, so I'm going to draw another box around D, like this. If we look at point D, there's going to be 2 forces on D, and I'm going to do them in purple. One, we're going to have our spring. Oh, that's never. Okay, perfect. One is we're going to have a spring force, which we don't know again. And the second, we're going to have a weight force due to this crate. But what's nice is since we know the weight of that crate, or the mass, sorry, we can find the weight. So if you guys just recall, a mass is something in kilograms, but a weight is a force. So a weight would be mass times gravity. So let's draw this free body diagram down here. And what we're going to do is we're going to call it free body diagram 2. And what we're going to do is we're going to draw our point. And it's actually probably good to label the points. So I'm going to call this one point A. And this one, of course, is going to be point D. And then what I'm going to do is I'm going to draw my two forces. So as we mentioned, there's going to be two forces on this particle. One going up and one going down. So what happens here is we know that the force going up is that spring force, that FAD. And the one going down, of course, is the weight of the crate. So this is going to be the weight of the crate, which is equal to the mass of the crate times gravity. And we know the mass of the crate is 2 kilograms, and of course we know gravity is 9.81. And now in finals and midterm situations, on the front of the examination, they'll tell you what value to use for gravity. Sometimes it'll be 9.81. Well, actually most of the time it usually is. But sometimes, of course, for simplicity, they say use 10. Just something easier for us to mark in. But it really depends. So what happens is when we solve this, what we get is the weight of the crate is 19.62, and this will be in newtons. So kilograms times an acceleration, so meter per second squared, is going to give you values in newtons. And if we were to look at free body diagram 2, so what I'm going to do is I'm going to put 2 here to show that I'm referencing that second free body diagram. I'm going to go sum of the forces in the y direction is equal to 0. And what I get is FAD going up, so it's positive, minus WC, so the weight of the crate, is equal to 0. So from this, we can find that FAD is equal to the weight of the crate, which is going to be equal to 19.62 newtons. So it's one of those things that you guys probably don't need that second free body diagram to find out FAD is equal to the weight of the crate, which is equal to this. And if I was in an exam, personally, what I would do is I would just draw the one free body diagram, and then what I would do right here is I would just go FAD is equal to mg, which is equal to 19.62 newtons. So it just kind of saves you guys that step. I'm just trying to show you guys, if you wanted to prove where that came from, this is how you prove it. But now we can look back at our original free body diagram, so free body diagram number 1, and we can see that we now know FAD, so therefore we only have 2 unknowns. And luckily for us, we have 2 equations. So this free body diagram becomes what we call determinant, meaning we can solve for those 2 equations. If we have more unknowns than equations, the free body diagram is referred to as indeterminate, which you guys will kind of see later. There are ways to solve indeterminate problems. Most buildings, the building you're in right now, I don't know which building you're in, but I guarantee the building you're in right now is indeterminate. And it's a very special reason why we like indeterminate buildings, but that's a story for another time. I know I can ramble on forever. So referring to free body diagram number 1, we have 2 equations. Our first is we're going to go sum of the forces in the x direction is equal to 0. So again, you don't have to go with x first. You can start with y. It's really completely up to you guys. I just start with x, and then I go y, and then I go a moment to finish. So if we look at this, we got FAB going to the right, so it's going to be positive. So we're going to have FAB, and this is the total force, so we need its x component, so that's going to be 4 over 5. So 4 over 5, and then minus FAC, So we're subtracting FAC because FAC is going to the left, which is opposite than our sign convention, which we see at the top corner over here. And then, of course, we want its horizontal component, which is 1 over root of 2. And we know that since it's in static equilibrium, the sum of the forces must be 0. And all that means, again, is nothing's moving. That particle, that point A right there, it's not moving. It's not going left or right or anything like that. And then real quickly, we can just rearrange this equation to get that FAC is going to be equal to 4 root 2 all divided by 5 FAB. And that's just simply moving one term to the other and then multiplying by that constant. So I'm going to go dot, 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 1. So this will be my equation 1. So if you hear me say equation 1, this is what I'm referring to. So our second equation is the sum of the forces in the y direction is equal to 0. So like before, what we're going to do is we're going to go up, And remember that according to our sign convention, any forces that go up will be positive and any that go down will be negative. So we got FAC and FAB going up. So what we're going to have is FAB and then the component of FAB, which is going to be 3 over 5 to get it into its y component, plus FAC plus its component, which is 1 over root 2. And then we have minus. So if we look at the minus sign, we have the FAD going negatively because it's going downwards. And it's just FAD. All of FAD is in its y component, so we're just going to go minus 19.62 is equal to 0. So again, if you guys are wondering where this came from, this right here, this is FAD. Just in case. So the next thing I like to do is I'm just going to separate the unknowns on one side and all the static, not static numbers, so I guess it would be static, but all the just kind of numerical numbers on the other side. So I'm going to go FAB and its component, which is 3 over 5, plus FAC and its component, which is 1 over root 2. And I'm just going to move the 19.6 to the other side, so we're going to go equals 19.62. And I'm going to go dot, 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 2. So this is going to be my equation 2. And if we look at equation 2, it's nice because we have a number on the other side. However, we have two unknowns. So what we need to do is relate one of the unknowns to the other and then substitute it in. So if we're looking at this case, what we're going to do is we're going to take equation 1. Oops, I zoomed in a little bit. We're going to take equation 1. We're going to take equation 1 and substitute that into equation 2. And by doing this, what we're going to get is this. So we're going to get FAB times 3 over 5, so that does not change because we're going to have everything in terms of FAB, plus 1 over root 2 times FAC, but if we look up here, we have an expression for FAC, so what I'm going to do is I'm just going to put a big bracket, I'm going to go 4 root 2 over 5, and the brackets, oh, and this is of course FAB, is equal to 19.62. So one nice thing that we can see right away, and this is something that you're going to want to start taking advantage of, is just getting rid of anything that you guys don't need. So we see that we have a root 2 here on top and on the bottom, so we can just erase it. So the next thing we want to do is we're going to want to factor out FAB. So it's just it appears one time. We don't want it to appear multiple times. So we're going to have 3 over 5 plus 4 over 5. And the bracket is equal to 19.62. And finally, we can divide both sides by everything in that bracket. And what we're going to get is that FAB is equal to 14.01, and that has a unit of newtons. So now that we have FAB, we can go back to equation 1 up here, and we can find FAC. So I'm referring to this equation right here in case you guys are wondering. And we can find that FAC value based upon what we have for FAB. So we know that FAC is going to be equal to 4 root 2 all over 5 times FAB, which we now know is 14.01. And what we get from this is that FAC is 15.86 and has units of newtons. So now that we have the forces in all of those springs, which is what we're after, we can start to find their stretched lengths using the spring formula, which I'm going to highlight in pink, is right here. So remember that stretch length that we want is delta x. So what we can do is we can rearrange this formula real quick and find that delta x is just going to be equal to the force of the spring divided by its k value. So if we go down here, what I'm going to do is I'm going to do this in a different color. So I'm going to go stretch length, so you guys know what I'm doing next. So stretched length. And let's start off with FAD. So let's start off with all the forces we know first. So we know FAD, and if we scroll up, is equal to 19.62 newtons. So 19.62 newtons. So therefore, delta X, and you should label which direction this is. So this is going to be AD, delta X, AD, is equal to force AD divided by KAD. And it's important to put this down so you guys know which K you're doing. So even though we know that this is 19.62 over, we look at the K's for the question that we're given, and we see that each one's a different value. So we got to pick the ones that we know relates to our situation. So KAD down here is equal to 40. So what we're going to do is this is going to be 19.62 divided by 40. And what we're going to get is that delta X AD is going to be equal to, that's going to be the 19.62 divided by 40. And what we're going to get is 0.49 meters. So again, it should have units of meters because that's the value from the spring constant. So if we look up here, our value is newtons per meter. So our value of delta X will be in meters. And then since that is one of the final answers, we're just going to put a quick box around it. Perfect. So now we can move on to the next one. So let's go FAB. And what we're going to do is just going to find out what that's equal to. And if we look up, we know that FAB is equal to 14.01 newtons. So we're going to have, 14.01 newtons. And then what we can do is delta X AB is equal to 14.01 divided by KAB. So if we look up to the very top, our KAB over here is actually going to be equal to 30. So 14.01 divided by 30. And what we're going to get is delta X AB. So the stretch length on AB is equal to 0.47 meters. So I'm just going to put a box because this is the final answer. Perfect. And then the last one that we have to do is FAC, which we know is 15.86 newtons. So delta X, that was a terrible triangle. Delta X AC is going to be equal to 15.86 divided by, and we're going to go up and find the spring constant for AC, and we see that it's 20. So it's going to be the 15.86 divided by 20. So what we get is delta X AC is equal to 0.79 meters. So there we go. This right here is the stretch length for all of the springs. So as you guys can see, the spring question is very difficult if you don't know the spring formula. What I've seen students do in the past for a situation like this is they'll try and solve for, let's say, L naught or L instead of the delta X. But one of the big things that I would say for this question that students would do is assume the same K value for all the springs. They'll usually find AD first, which is what we did, and we know that the K value is 40. And then for the next two, they'll just put 40 and not realizing that each spring could have a different K value. But other than that, like I said, it's not too bad. What I want to do for you guys in the next example is we're going to cover, and I'm going to just highlight in pink so you guys know what I'm talking about, is kind of this formula here. Because like I said, right now we were kind of lucky because all we wanted to do is find that delta X. But most of the time in the lab, or especially midterm, we're going to have to go further than that and find either one of L or L naught. So that'll be the next example, so don't be too worried. So with that being said, thank you guys so much for listening, and I will see you guys in the next video.